I wanted to do. All right, we're ready to rumble here. First thing we want to talk about. Oh. Was it an Excel file? Okay. Okay, let's check it after class then. Yeah, cool. Look at you guys working on lab 4 already. Can't keep up with you guys. You'll see there's a Dropbox for the labs. That's because, well, there were some updates to the question, so I had to re-import it, and then all the other stats labs have to submit their Excel worksheet, right? I don't really care. I guess I should have not recorded that. No, I care very much, and I will look at all of them. Right, and so all you have to do is just submit your Excel sheet that you've been working in. It can be empty, I don't care. But especially for lab 4, because some of it you can just probably do by hand, right? And so you absolutely could use Excel, right, as your calculator, that kind of thing. But as long as you've submitted an Excel sheet, then it should open up the lab. We'll see if that's the case here.
It just says it has to be marked.
Oh, so then you check it off? Yeah, if you go and check it off and say done, then yeah. So okay. I'll just summarize here. So for the labs, you will need to submit your Excel sheet before you can do the quiz. Before you can do the quiz. We'll see how it works out. Just, yeah. Yeah, so the idea is that you're supposed to work through those exercises at the end, do all that work, submit that, and then just use that work to do the quizzes. It's just to make sure that you've done those exercises. But you would do it like, yeah, because those exercises just give you everything that you need to do the quiz. Like I said, I don't really, I'm not going to look at them. So just do what you got to do, okay? Wink. So there's that kind of added obstacle, but I think once we figure it out, then we'll be good. Okay. It seems that you have to mark it complete, but you should just be able to check it off, but we'll see. We'll see. Okay, what else did I want to say to you? Oh yeah, we're just about to wrap up probability chapter 5, right? We were working on a tree diagram. If you don't have the chapter 5 printouts, I still have 4 more. So if you don't have a printout, you can come get it. Also, I've got some formula sheets here. Okay. So how about we just keep going with what we were working on last day, right? Because we said let me see if I can steal all of this. Because you've got it in your notes, so may as well save ourselves some time here. Example continued from last day. And I guess I could steal the actual question. Copy. Oh, come on. Where am I supposed to paste this? Put it here, but. I guess it should have gone above, but that's okay. We'll survive. So the question that we were working on was we had to build a tree diagram, and we said, okay, well, often we'll have probabilities, right? Consecutive probabilities. So one thing has to happen, and then another thing has to happen, and then another thing can happen, and another thing can happen. And so as soon as we're saying and, right, this and this and this, right, we've got these consecutive things going on. So to organize that work, we usually build tree diagrams, and we said, okay, well, in our example, we learned that 13% of students earned an A on the midterm, and of those students, 47% got an A on the final, and then 11% did not get an A on the midterm, but got an A on the final, right? And so here, right, we set up our tree diagram, and we kind of made some rough notation. It's tough because we said, well, both of these are talking about getting an A on the midterm, A on the final, right? So instead of using A and A, right, doesn't really make sense. So then we said, okay, well, I'm gonna let M be an A on the midterm and F be an A on the final, right? Even though that might be hard to think about that way, right? But that's the notation that we're using. And so what we're gonna say is we've got our kind of first layer, as I like to call it, is the first thing that has to happen, right? First, we have to write a midterm. There's only two ways that we can go if we're just talking about getting an A or not getting an A, right? And we know the probability of getting an A on the on the midterm is 13%, right? And so the probability with that first branch with the M is going to be 0.13, right? 13%, but probabilities, when we're doing math with probabilities, we have to use the decimal notation. Okay? And so we're going to use 0.13. And from that, we know that the probability that they didn't get an A on the final, or on the midterm, keep saying final, on the midterm, is 1 minus 0.13, 0.87. Okay. So we only need to know a few of these probabilities to be able to figure out what the rest of them are as well. Okay. For the rest of the probabilities, right, we've got, of the ones who got an A on the midterm, 47% got an A on the final. So now we're down in the second event, right, the second kind of layer of our tree diagram. And so getting an A on the final, if you got an A on the midterm, right, so given that you were given, that you got an A on the midterm, the probability that you got an A on the final, we're told is 0.47. So down here, we've got a probability of 0.47. Okay. Which means if you got an A on the midterm, but didn't get an A on the final, what's the probability of that? It's going to be 1 minus 0.47, 0.53. Okay. So each set of branches have to add to 1, right? So then, if we didn't get an A on the midterm, 11% did not get an A on the midterm, but got an A on the final, right? And so here, they didn't get an A on the midterm, but there's 11% of them that got an A on the final. And so 11% puts us at 0.11. And then 1 minus that is 0.89.
Is that 11% of all students did not get an A on the midterm but got an A on the final, or 11% of students who did not get an A on the midterm but an A on the final?
It's given that they got, so it's not really clear, but it's given that they didn't get an A on the midterm. The probability that they got an A on the final is 11%.
Okay.
Yeah, wording's a little bit wonky though. Yeah, good catch. So here, let's make a note of some of the things that we've talked about, right? To use probabilities in math, we must use decimal notation or decimals, right? We can't use the percentages to do the math that we want to do. Okay? So that's important. And then each of these branches or sets of branches have to add to 1. Right? All the total probabilities, right, at each step have to add to 1. Where can I put that? The total probabilities for each branch, I'll say. For each branch must add to 1, right? Which makes sense if you think about it as, okay, well, here, right, I'm starting and I write my midterm. There's only 2 ways that this can go, right? I either get an A or I don't, okay? And so those probabilities are the only possible things that can happen here. And so the total probability there has to add to 1, right? But now, if I got an A on the midterm, now I'm standing here at this junction and I'm looking down, okay, well, I could get an A on the final, or I cannot get an A on the final, right? But for me, those are my only 2 outcomes, right? So these probabilities have to add to 1. Same thing for these guys. They're only looking at 2 possible outcomes, not probable, well, 2 possible probabilities too. And so these 2 have to add to 1. Okay. What we said last day was, okay, well, what if we're interested in the combinations, right? What's the probability of getting an A on the midterm and an A on the final, right? To end up at this probability, right, an A on the midterm and an A on the final, which we can denote by just switching them together. If you're saying and, you're going to be multiplying probabilities. And so the probability of getting an A on the midterm and an A on the final is going to be 0.13 times 0.47. Right? So at the end of all of these, right, at the end of each branch, I guess, you're going to be multiplying the probabilities that run down the tree. Okay? To find the probabilities at the end of each branch, we multiply the probabilities. Can I say that take you there? Does that make sense? I kind of run down those branches, right? And so we multiply the probabilities, that I'll say that go down each branch. So now, if we kind of recreate this, because I don't want to keep scrolling up, I can say that the probability of M, we said was what, 0.13? The probability of the complement of M, just to reiterate, is 0.87. Down here, this is the probability of F, but to end at this branch, right, you have to have had an A on the midterm, right? So this is technically the probability of F given M is 0.47. The probability of not F given M is 0.53. I got to scoot these over a little bit. Oops. Because here, the probability of getting an A on the final, given that they didn't get an A on the midterm, we're told is 0.11. And then here, the probability that they don't get an A on the final, given that they didn't get an A on the midterm, we said was 0.89. If we think about these conditional probabilities, right? We talked about the general multiplication rule. Where was it? Formula sheet here. Right. And so, oops. Here's our formula sheet, right? Or at least the relevant bits here. If we know the probability of A given B, right, that's when we're allowed to use the formula, the multiplication formula, right? Because if I want the probability of A and B, right, getting an A on the midterm and on the final, right, I need to know the conditional probabilities of one of these, right, of the later event. So in this case, right, the probability of getting an A on the mid or on the final, given that they got an A on the midterm, times the probability of the A on the final. What this is just going to translate to, though, is just multiplying down each branch. Yeah. And so what we get is we get, for this one, the probability of M and F is going to be the probability of F given M times the probability of, oops, sorry, M. Which is just 0.13 times 0.47. So 0.13 times 0.47, I get a probability of 0.0611. That's the background stuff that's happening, right? We are using conditional probabilities because we separated everyone at the top branch, right? And then the next probabilities are conditional on what happened on the midterm, right? Did they get an A? Did they not get an A? So for each of these, the rest of these probabilities, just keep in mind that you're talking about conditional probabilities, but you don't actually need to show it. We can just say that the probability here, just because I'm running out of, I don't have a lot of space on here. but the probability of getting an A on the midterm and not getting an A on the final is going to be 0.13 times 0.53, 0.13 times 0.53, 0.0689. Notice that I'm going to keep all my decimal places, or at least as many as you can, because at the end of the day, every student in a class has to be at one of these ends of the branches, right? They wrote a midterm, they either got an A or they didn't. They wrote a final, they either got an A or they didn't, right? And so the total probabilities at the end of all these branches has to be 1, right? Because that's all the possible outcomes. And so again, all these have to add to 1, and that's how you're gonna check it. But you can't, it's not gonna add to 1 if you've rounded, right? So you wanna keep that in mind. And so the total probabilities at the end of all the branches must add to 1. So then, if we go up here, whoop, glitchy, the probability of not getting an A on the midterm and getting an A on the final is 0.87 times 0.11. Uh-oh, run out of options here. Yikes, looks gross. Hopefully you've got more room on your page. Make it look nice. I get 0.0957. And then put this guy down here. Nasty. The probability of not getting an A on the midterm and not getting an A on the final is 0.87 times 0.89. 0.87, oops, not 0.57, 0.87 times 0.89. I get 0.7743. So now, if I add all these probabilities just to check, oh my doodads up here. All these probabilities, so 0.0611 plus 0.0689 plus 0.0957 plus 0.7743 plus 0.0957 plus 0.0689 plus 0.0611. They all totaled 1, which means I didn't flub it this time. Good. So, right, which also means if we're saying or, so here we said that, okay, if we've got these consecutive events, then this and this happening, right? When we're saying and, we're going to be multiplying probabilities. If you're saying or, so if they got an A on the midterm and got an A on the final, or got an A on the midterm and didn't get an A on the final, we could find that probability by just adding these probabilities, right? Because the total probability is going to be this, or this, or this, or this. So then we're adding, right? And so, so you want to be really aware of what you're saying when you're talking about these probabilities, right? And so, When calculating probabilities, if we say A and B, right, whatever they are, we multiply the probabilities. Which we saw in the formulas up here, right? If we're talking about the probability of A and B, depending on if they're conditional or not, right, we're going to be multiplying probabilities. Right? Whereas if we say we want A or B, whatever the events A and B are, we add the probabilities. So just as a little kind of, I don't know, switch in your mind, right? If you're saying and this and this and this has to happen, then you're going to multiply those probabilities, right? If you're saying, oh, this or this can happen, then you're going to add those probabilities, right? And so it's on your formula sheet. We already talked about it, right? But I'll throw it on here as well. We can see that we do have to subtract the overlap if there is any, but in this case, the branches are all going to be disjoint, right? And so that's why we can just add and add and add and add. There's no overlap. Nice. So I'd say those are the things to keep an eye out for. What do I want to look at here? I guess I kind of ignored the questions. Build a tree diagram, labeling all the appropriate probabilities. Well, that's what we did here. The probabilities of each branch, and then at the total each branch. What's the probability of a student earning an A on both the midterm and the final? Right? We know that as the probability of M and F. Right? The only time that happens is the far left branch. Right? And so now we know that the probability of M and F is 0.0611. It's the probability of a student earning at least one A on either the midterm or the final, right? And so now we're going to look at all these outcomes, and we can say, okay, well here, and we just count wherever they got A, right? You could follow down the branches, right? But here they got an A on the midterm and on the final, so that one satisfies the criteria that we're looking for. Right? Or this one, because they got an A on the midterm, not on the final, but we're just looking for at least one A, right? Or this one, they didn't get an A on the midterm, but they did get an A on the final. Right? And so what we could do is we could add these three probabilities, or if it's easier, then we said, okay, well, they totaled one. The only time that they didn't get at least one A is when they didn't get an A on the midterm and they didn't get an A on the final, right? So what you could do is you could take 1 minus 0.89 to find the total probabilities on that side. Right? Take the complement of getting at least one A. So I guess I should move this down. Copy. Hey, kept it all. Nice. the probability of at least one A is the probability of an A on the midterm and on the final, plus the probability of an A on the midterm and not an A on the final, plus the probability of not an A on the midterm and an A on the final. Or, if it's easier, you could say 1 minus the probability of not an A on the midterm and not an A on the final. Just depends on what you prefer, right? Do you want to just add the probabilities that satisfy what you're talking about, right? In this case, getting an A on either the midterm or the final. Thinking about this one, this is essentially the complement of at least one A. It's the opposite of at least one A is not getting any A's at all. Whenever I can, I like to use the 1 minus, less math, right? 1 minus 0.7743. One minus 0.7743. I get 0.2257. It's that probability. What's the probability of a student earning an A on the final, but not on the midterm, right? There's only one branch that satisfies that criteria, right? We have to get an A on the final, which you could start and say, well, to get an A on the final, that's these two branches, right? These two, they didn't get an A on the branch, or on the final, right? But here they got A's on the final. But now we're adding the criteria that, okay, well, they didn't actually get an A on the midterm, so then this one's out, and the only probability that satisfies that is the third branch. So question 4, the probability of not getting an A on the midterm and an A on the final, we said was what? 0.0957. So to answer all these probabilities, right? Once you've built your tree with all your probabilities on it, it's going to be a lot easier to just look at these and say, okay, well, that's going to be this branch that satisfies this. If you want to add multiple branches, right, then you're just adding those probabilities at the end. Okay. And so the key is, and I overcomplicated things, but it's the truth, so there's no way around it, right? These are conditional probabilities that we talked about last day. But in your mind, right, just so it's not overly complicated, I just want you to think about, okay, well, if I need the probability at the end of each branch, right, which is going to be this and this, I'm just going to multiply these probabilities. Multiply, multiply, multiply. And then to check your work, make sure they all add to 1. Right? Otherwise, you've done something wrong. Yeah. As soon as we have these consecutive events, then you're going to build a tree diagram, right? So first this happened, then this happened, then this happened, then this happened, right? But we're going to stick to just 2 layers, right? First event, second event, If there is a first event and the same people, let's say, or animals or whatever, are doing the next event, you're going to have conditional probabilities, right? So as soon as we've got these consecutive events, well, we're going to have these conditional probabilities in the second layer, right? You will have a tree diagram on the test, right? But it will say, build a tree diagram, labeling all the appropriate probabilities. Chunk of marks there, right? And then the next few questions, just like we did here, you're just going to work through, figure out what the probabilities that you want are, right? Show your work. But most of the time that you're going to spend on this question is on the tree diagram, right? Because that's where you're going to pull all your work from. So we'll have to do one. It's going to be okay. We will survive. Okay? Yes. Yes, you will. So I'll give you a practice. Sometimes I find them a little bit deceiving if it's just problems, because then you go home and you work on those exact problems, and then you get into the test and you're like, hey, that wasn't exactly like what I did at home. Well, no, obviously, right? And so what I want to do, I give you a list of concepts, right? And then I show you how those concepts might be tested, right? Just to give you an idea of kind of what to expect. Okay? And so it'll be kind of a list of concepts that I need you to know for this test, and then some example types of problems that test the same thing. Right? So, but yeah, I was kind of toying with putting chapter 6 on there, or at least 6.1, 6.2, but I think we'll cut it here because the test is on Wednesday, right? And so we will start chapter 6, which is on the normal distribution, but the test will be up to here. Okay? So my notes are all over the map today. I feel like it's because I pulled in from last night. Yeah. Yes, it'll be sometime this week. Yeah, because I was kind of going back and forth on including chapter 6, which means cutting some of the earlier stuff. But now that we're not doing chapter 6 on this test, I can put some more stuff on. So anyway, so it was kind of up in the air. I talked to Joy, who's teaching another section. She was like, oh no, I'm not putting chapter 6 on. Good, because I won't have time to get there anyways. So, but let's put, so maybe I'll put it in, well, I don't like red, so we'll use pink. Red is like bad. Test number 1 material will be up to this point. How's it looking? No bueno. Okay. I feel like this was plenty of material anyways, right? We talked about how do we summarize data, how do we collect data, right? Those are 2 kind of big players. And then we talked about things like numerical summaries. Yeah. No, I know. Usually I do, and I would love to, but I don't have time. I know. I'm trying to squeeze all this material in.
On the last time, we did the review, people finished
Yeah. I mean, if you have questions about the review, because you'll have the review by Friday, then you can use the lab time to ask questions about the review. Yeah. And even on Monday, we see each other Monday, Wednesdays, right? Even on Monday, we could take a little bit of time to go through if there's any kind of pressing questions, right? Then we can take some time, right? Because I would love to do a review, but cramming all this material in here. So test one up to this point. So basically, like, turn off your brain from now on, I guess, for the test. It will be on test 2, so it will come back, but I know, which I also hate doing, but anyways. So you will have a practice document, let's call it. Review document. But, oh crap. Forget what I said. I need more time. I know, you used all your highlighters, did everything. I forgot. There's 2 more itty bitty sections in here. Don't turn off your brain yet. Stay with me. So, good thing I have my notes. Usually I just kind of go off memory, but ugh, doesn't serve me well. Hey, no one asked me about 5.3 and 5.4. What about these sections? And I was like, I'll never tell. 5.3 is just kind of touching base on a special case. So sampling from a small population. Sampling from a small population. Whoops. Oh, the Mexicals is going on here. There. If we've got a small population, and this doesn't happen very often, right? Usually we're sampling from very large populations, so it's not even an issue, right? But if we're sampling from a small population, then we have to keep in mind that it's very important whether we're sampling with replacement or without replacement, right? Because if we're sampling with replacement, then I'm pulling people out, and then for my next sample, I'm putting those guys back in, and then I'm pulling a new sample, which means that I could be drawing from the same people, right? If I'm drawing from a large population, then that's not going to happen so much as long as I'm not pulling too big of a sample, right? So it doesn't actually matter if I'm doing it with replacement or without replacement. And so if sampling from a small population we need to be aware of whether we're sampling with or without replacement, of whether we are sampling with or without replacement. Okay. If we're sampling with replacement, hopefully you can read that. Anyways. With replacement, then we can assume that these probabilities are going to be independent, right? Everyone's independent from each other, and so then we can assume, oops, you assume, wow. We can assume the probabilities are independent. Are independent. That's important, right? Because if we're finding the probability of this and this, if they're independent, right? If we know they're independent, or we can assume that they're independent, we can just multiply those probabilities, right? Whereas if they're not independent, then we have to deal with the conditional probabilities, right? And use those formulas. And so without replacement, the probabilities are not independent. The probabilities are not independent. And we use this example to introduce conditional probabilities as well, right? But think about a deck of cards, right? If I'm pulling 4 cards, right, no matter what they are, and then, so those probabilities are independent, right? Because I've shuffled and whatever, there's no reason to think that some cards would cling together more than others, right? So I just pull 4 cards randomly. We can assume that those probabilities are independent. If I put them back in, right, then whatever card I pick, blah, 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 they're all independent. If I pull them out and I put them to the side, and now I'm drawing from this deck with some cards removed, right, then the probabilities are not independent of what happened over here, right? The probability of pulling a diamond, for example, is going to depend on what I pulled here. If I pulled 3 diamonds, for example, then the probability of pulling another diamond is lower, right? Or if I didn't pull any diamonds, then the probability of drawing a diamond is a little bit higher than all the other cards, right? And so if you're doing with replacement, then all the probabilities, you could assume they're independent. If they're without replacement, right, so we're pulling some, putting them to the side, they're not in our population anymore, then the probabilities are not independent. Mm-hmm. Yeah, for small populations. For larger populations, in the grand scheme of things, it actually doesn't matter. Okay? And so when the sample size is only a small fraction of the population, right? And here we're actually going to say under about 10% of the population. What are we saying here? If we've got a sample and we're able to draw just a reasonable sample size, but it's less than 10% of the population, basically what we're saying here is that we've got a large population that we're dealing with, right? And so we have a large population is kind of what we're saying, or it is what we're saying. Hey, large. Then observations, we can assume that they're nearly independent, right? Regardless of if we're drawing with replacement or without replacement, right? So and so observations are nearly, are nearly independent even if sampling without replacement so it just depends on if you're pulling from a small population or a large population. This is kind of counterintuitive because probably coming into this course, the one thing that you did know was, oh, well, I have to have a large enough sample size, right? Small samples are bad. And so now we're kind of putting on a restriction. So yeah, we want large samples, bigger samples, bigger the better, right? But now we're putting on another restriction and saying, okay, well, if I'm able to draw less than 10% of the population, then I'm able to assume that all these observations are independent of each other, which is going to be one of our assumptions later on in the course, right? And so this is going to come back. And so we'll say, do I have a big enough sample? Great. Also, did I pull from less than 10% of the population? Good. That's my kind of sweet spot here, because then I'm able to say, well, this sample is representative of my population, but also I can assume that all these observations are independent, right? So it's kind of like this trade-off, right? You want big samples, but not too big. And so, but that'll come back later. And so we'll parking lot this for now and talk about, I keep scooting that down. So disappointed with myself. Forgot about 5.3 and 5.4. Five 5.4 is just about random variables. And we'll talk more about random variables, but we'll just talk about the general idea of them in this section, and then we'll come back to it. So a random variable is a numerical variable whose values depend on a random outcome, right? Or so a numerical variable whose values depend on outcomes, just kind of fancier, of a random phenomenon, phenomenon. Fun to say. Phenomenon. Random variables are often denoted by capital letters from the last bit of the alphabet, usually starting by a capital X, Y, Z. We've seen for observations, right? We usually use a lowercase x and a lowercase y to start off with, right? So here we're just talking about any random variable, right, that'll generate little x's and little y's. So here, we've already talked about the mean of x's, right? We often say that that's our expected value, right? And that's not that far-fetched, right? If we're talking about some set of outcomes, then if I asked you, okay, well, if you were to do this again, what would you expect to see? You would probably expect to see things around the mean, right? And so the mean of a random variable, we usually call it the expected value of that variable. Scoot it down again. Oh man, should just delete it. No, that's admitting defeat. I won't delete it. Never. We often call the mean, oops. We often call the mean of a random variable sometimes we denote it just RV, random variable, right? I only mention that because if you're kind of Googling stuff or whatever, usually they just say RV, right? So random variable. So we often call the mean of a random variable the expected value. The expected value, or E of X, which you're going to read as E of X E of X is the expected value of X, where X is some just random outcome generating, or random phenomena generating outcomes rather. So the way we've been calculating the mean assumes that all the possible outcomes have the same probability, right? That's not always the case, right? We saw from those probability distributions that, okay, we could have some outcomes that have a higher probability of happening than other outcomes, right? And so we have calculated the mean right, and called it X bar. We could also call it E of X, that's not wrong, right? But usually we just call it X bar. So we've calculated the mean. But we assumed each outcome had the same probability, right? So the probabilities were distributed evenly across all the outcomes. But we assumed each outcome had the same probability. For example, right, if I ask you to find the mean of 1, 3, 9, and 7, you can do that. Right? I won't give up. So find the mean of 1, 3, 9, and 7. Then we could say, well, X bar is 1 plus 3 plus 9 plus 7 divided by 4. Right? 1 plus 3 plus 9 plus 7 is 20 divided by 4, puts me at 5. So therefore, the expected value of X here is 5. Okay. What if I gave you, right, because now each of these outcomes, right, 1, 3, 9, 7, we're saying they each have a 1 in 4 chance of happening, right? What if I gave you a probability distribution that said, actually, here are the probabilities instead? So now, consider instead the following probability distribution. Oh man. So now I've got my X is 1, 3, 9, or 7. If it bothers you, you can rearrange them, right? But it doesn't matter. So here are my outcomes. And then I'm going to tell you that the probability that X equals Xi, so capital X equals lowercase xi, and that's just notation. It's just saying that, hey, this is actually X1, X2, X3, and X4. the probability of each of these, right, in a probability distribution, well, we know each of the probabilities have to be between 0 and 1, and they have to add to 1, right? Each of these outcomes are disjoint, so we're good on that front, right? So here, if I give you the probability distribution, so the probability of a 1 is going to be 0.3. The probability of a 3, let's make it 0.2. And probability of a 9, let's make it 0.1. And then 0.1 minus 0.3 minus 0.2 minus 0.1. The remaining probability must be 0.4, right? Because I know they have to add to 1. Yeah. That's a question too. What's the missing probability? Right? Then you just have to figure out, well, you have to remember that they all have to add to 1. Then you can just find the missing probability. Right? So now I'm saying that, okay, well, each of these have a different probability. But what you're going to do is you're going to say, well, 1 happens with a probability of 0.3. So then you have 1 times 0.3 plus 2 times 0.2 plus 9 times 0.1. And then you just multiply each of the x's by their individual probabilities. Right? And so what we have is E of x is going to be x1 times the probability that x equals x1 plus x2 times the probability that x equals x2 plus x3 times the probability that x equals x3 plus, should have squished this over, plus x4 times the probability that x equals x4. So what we get is 1 times 0.3 plus, 3 times 0.2 plus 9 times 0.1 plus 7 times 0.4. So I get 0.3, 3 times 0.2, 3 times 0.2, so I get 0.3 plus 0.6 plus 9 times 0.1, 0.9 plus 7 times 0.4, I get 2.8. My expected value here, if I add these all up, is 0.3 plus 0.6 plus 0.9 plus 2.8. 4.6. Now, we're going to disregard the problem of, well, I actually can't get 4.6 in here, but that's what I'm expecting, right? So usually we talk about kind of gambling situations, right? Knowing that the expected value is 4.6, which one would you put money on? Probably 3 or 7, right? Looking at these individual probabilities, probably 7, but 3 might pay out more. Anyways, the expected value is 4.6. So the expected value can definitely be a value that's not a possible outcome. It's just what you're expecting to see, right? And so, although 4.6 is not a possible outcome, it is the value we would expect to see I'll add on in the long run, but we won't worry about that. So what we've got here, and if each of these probabilities were the same, right, then we would have each of them, all the probabilities would be 0.25, 0.25, 0.25, 0.25, right? But you would end up doing the same thing. Right? So now we're just changing those probabilities to be different for each of the outcomes and finding the expected value what this looks like on your formula sheet, right, is on the top right-hand side. Is that the expected value of x, so we can write the expected value of x is the sum of each of the xi's times the probability that x equals xi. That's what we did, right? We took each of the outcomes, multiplied it by its probability, and then added those all up. This assumes that we have a probability distribution, right? And so I have to give you a probability distribution to make you find the expected value this way. We can also find the variance, and I actually like the second version better. So given a probability distribution, we can find the expected value of x as well as the variance of x. And then you could take the square root of the variance to find the standard deviation, but we'll stick to the variance for now. Using this formula here, I know this is a stretch, right? But the sum of the xi squared, so now you're just taking the x's, each of these x's squared, but then you're multiplying them by the same probabilities that you had before, right? And so what we can write that out as is the expected value of the x's squared. So the variance of x, we're going to use the sum of the xi's squared times the p of x equals xi minus the e of x squared. E of x, that's just the mean, so you just square it. Right? So that last term is fine. But here, if we notice that this is the same as the expected value of x squared, and to find this, right, calculate a new row of all the x's squared, which should sound familiar, right, from finding the variance and the standard deviation for any data set, right? So all your x's squared, then find the expected value, oops, then find the expected values. So for example, if I want to find the variance of these guys, copy. Come on. What am I going to do? I could make room below the x's, but I'll just make another row of the x's squared. 1 squared is 1. 3 squared is 9. 9 squared is 81. And 7 squared is 49. So now, if we want the expected value of x squared, well, that's just going to be each of these squared values times the probabilities, right? So then we have 1 times 0.3 plus 9 times 0.2 plus 81 times 0.1 plus 49 times 0.4. Which is going to be 0.3 plus 9 times 0.2 is 1.8. 81 times 0.1, 8.1. 49 times 0.4, 19.6. If I add these up, 0.3 plus 1.8 plus 8.1 plus 19.6, I get 29.8. Now I can find the variance of x if I just use the expected value of x squared minus the expected value of x squared. Those two are different. Because now I have each of these components, 29.8 minus the expected value of x was 4.6. 4.6 and then squared. So first I have to find 4.6 squared. I get 29.8 minus 21.16. I get a variance of 8.64. Therefore, the standard deviation of x is the square root of the variance of x, square root of 8.64 is roughly 2.939. Oy. Okay. So this is only if I give you a probability distribution with different probabilities, right? Then we can use those to find the expected value of x, which is just the mean of x, and we can find the variance of x using this formula, right? And so, and of course the standard deviation of x, because it's just the square root of the variance, right? And so, but it does assume that I give you a probability distribution. If I just give you a set of values and ask you to find the mean and the standard deviation, then you just do what you've normally been doing. Okay? Test 1 up to this point. There. Final answer. Any questions? No, that was too much. I know. Nice work. See you guys on Friday. Bye, guys.